Okay, so now that we're done with chapter 4, it's time to do some practice problems. So let's do that right now. So this is the problem set. So you can see that we have 15 integral problems to work on, and it's a mixed bag. There's a little bit of everything here. So that's kind of the challenge of doing this, that we have to know how to recognize which type of technique we should be using in each case. And often we'll discover that the method of substitution is often the way to go, but not always. Okay, so first things first, let's look at this one. And often our best approach is to basically split this up into separate integrals, because then each one might be easier to integrate individually rather than trying to do it all at once. Okay, so let's rewrite this one as integral of e to the 2x dx minus 1/2. And you notice here I am putting the constant on the outside because that often helps us identify what technique we're supposed to use here. All right, now for both of these, it looks like what we want to do is find the form integral e to the u du equals e to the u plus c. All right, we need the c because these are indefinite integrals, meaning that if you notice, there's no lower and upper limits of integration. So we call this an indefinite integral, which means it's covering the entire domain of the function. Now, here's the thing, though. We have to often rewrite our integral to put it in this form, or the form that we're looking for. So here's a perfect example of this. Let's start with the first one. Integral e to the 2x dx. Suppose that I decide to let u be 2x. Du dx would therefore be 2. Du would be 2 dx. And guess what? We have, if this is where we're going, we have e to the u. We do not have du inside the integral, but we can easily create it by doing the following. We can do what's called supplying a constant. In other words, I'm going to algebraically rewrite it as 1/2 e to the 2x 2 dx. So in other words, I'm multiplying by half and dividing by multiplying by 2, so that I end up with the same exact expression, except look what this lets me do. All of a sudden, I've got what I'm looking for, e to the u du. This is my du. This is e to the u. Now, of course, you'll recall from the slides that e to the u, the integral of e to the u, is very simply e to the u plus c. And by the way, there is a table in the back of the book, so let me show you real fast, where all of these functions are found. Okay, the integration tables are enormous. Look at this. Let's see how many of them there are. Ooh, there's 100, and there's more. They're just showing you 100 of them. So if you're not sure, here it is right here. E to the u du equals e to the u plus c, number 81. And if u is equal to x, well, then it's just e to the x ends up being e to the x plus c. So u can be any function of x. Okay, so that means that the integral of this first term because it's already in the form e to the u du ends up being 1/2 e to the u plus c. And of course, now we're going to replace the u with its definition, which is 2x. The second term is negative 1/2 e to the x to the 1/2 over 2. All right, let me just copy this. Sometimes it lets me copy, sometimes it doesn't. All right, I'll do this instead. So now we have to be careful. At the end, we have to bring these back together again. So we have our first result. That's the integral of e to the 2x dx. Okay. Now for the second one, minus 1/2 e to the x over 2 dx. So here we can try letting u be x over 2, which means that du dx is simply a half, which means that du is 1/2 of x. All right, well, guess what? We don't have 1/2 of x. However, we're very close to having 1/2 of x. In fact, the only thing that throws it off is that we have a negative here. So let's try this. So you can see all I did was rearrange this expression algebraically. It's the same thing, but all of a sudden, look what we have. We have negative e to the u du. And so this time u is defined as x over 2. So now we can just bring these together and we'll have our final result. Okay, so the final answer, just copy this down here again, is the sum of the two terms that we just derived. So in other words, we'll have 1/2 e to the 2x plus c minus e to the x over 2 plus c. Now the c's can be literally anything. What we normally do is we consolidate them into a single constant. So we end up with 1/2 e to the 2x minus e to the x over 2 plus c. And that's that's our final result. Now, if you're not sure that you've done this correctly, it's a simple matter to take the derivative of the result and make sure that it matches what you're seeing here. Okay, so we don't have to do this every time, but just for this one, why don't we go ahead and do our double check? We don't have to worry about the constant because its derivative is clearly equal to 0. Okay, so let's break this up into two derivatives. So you might recall that based on the chain rule, the derivative of e to the g of x is e to the g of x times g prime of x. Okay, so what will that tell us for the first term? So we'll rewrite this as 1/2 of the derivative. It's usually a good idea to get constants on the outside because they tend to be distracting and makes it harder to see what we're doing. So in this case, g of x would be 2x and g prime of x would be the 2. So this term by itself will be 1/2 e to the 2x times 2, which means e to the 2x. This one will be, so we got minus d dx of e to the x over 2 power. And so here g of x would be x over 2, g prime of x would be 1/2. So therefore, this is equal to negative e to the x over 2 times a half. or minus 1/2 e to the x over 2. So if our original function was, if f of x that we started out with is e to the 2x minus 1/2 e to the x over 2, then we're all set. So let's make sure that that's the case. I'll just copy it down here. And we'll see whether we did it right or not. And the answer is yes. Okay, so all of this was not necessary, but especially when you're first learning something, double checking is probably a good idea. Okay, so I'll put a big check mark here to indicate that we did it correctly. All right, now this one, what's going on here? Well, this is one of those cases where, again, you probably would want to split it up into two terms. Often, a single term like this is going to be too complicated by itself, unless it happens to have a specific form, like later on when we're looking at the arctangents, for example, and those, it might be better to leave it like this. But for now, with the polynomial in the numerator and the denominator, why don't we try this? Okay, so that means we have now, and oh, by the way, what we could also do is this. Um, I'll tell you what, let's leave this one the way it is because you might recognize it if I write it like this. The second one, let's write it like this. Why am I doing this? Because you recall from what we did earlier that the integral here of dx over x, or simply 1 over x dx, is equal to log x plus c with the absolute values. So the first term here is going to be log x, absolute x plus c. Second term, we can use the power rule. Okay, so remember how that works with integrals. The power rule for integrals is x to the n plus 1 over n plus 1 plus c. And of course, this is assuming that n is not equal to -1. If it is, then we'll end up with log absolute x plus c. And that's what happened here. So what about the second term? Again, we can use the power rule for this one, minus x to the minus 2. If n is -2, then n plus 1, of course, is -1. So we end up with negative x to the -1 over -1 plus c. Or we can simplify this a little. These negatives cancel out, and we're left with x to the -1, or simply 1 over x, plus c, of course. So we consolidate these. Here's the result of the first part, the second part. So the final answer is log absolute x plus c plus 1 over x plus c. And again, as always, we just simply consolidate the two constants. And there we go. All right, so the strategy here was to break up this ridiculously complicated looking expression into two terms, which could be simplified further, and then we can figure out what rule to apply to each one. The first one is the log definition. The second one requires the power rule. Okay. So now, oh boy, now this one's a little challenging because we've got trig functions and it's a definite integral, meaning we're going to need to solve it for a specific value. So let's break this up. Okay, so this one isn't actually that bad because, first of all, the power rule applies here. We end up with x squared over 2. Now, because this is a definite integral, we don't have any constants. Evaluated over the interval from 0 to pi over 2. And then here, now, this is where we have to be careful. You might recall that the derivative of the cosine of x is the negative sine of x. So it looks like we're going to wind up with cosine x evaluated from 0 up to pi over 2. Now, if you're not sure, all you have to do is go to this chart and look for the integral of sine x, wherever they've put it. And you'll see it is negative cosine x. Okay, so if you notice, if you went to the chart, you would have had negative cosine x. Okay. Um, hold on, let me just make sure. Yes. Okay. So I just realized I left out the negative here. Yes, the integral of sine x is negative cosine x. So I almost goofed it here. You see what I've got? This has to be negative. All right, now we can just evaluate. So I have pi over 2 squared over 2 minus 0 squared over 2. Over here we have minus cosine pi over 2 minus a minus cosine 0. Okay, so here we have pi squared over 4 over 2 minus 0 plus cosine pi over 2. And then the two negatives here and another one here. This is negative cosine 0. Okay. Well, now, unless you have these memorized. Now, this one, by the way, can be simplified to pi squared over 8. Cosine of pi over 2, if you have your handy calculator here. By the way, if you're using your calculator, make sure you're in the radians mode when you do this calculation. We're going to take the cosine of pi over 2, and that's 0. Okay. Cosine 0 is 1. So we end up with pi squared over 8 plus 1. Okay. All right. Now, what's next? Ooh, now this looks like a headache coming our way. But when you see a product of two polynomials like this, the first thing you should always think about is maybe this is a good example of the substitution effect, using the substitution method, because it kind of has that look like it looks like the chain rule has been applied to something here. So we're going to use the method of substitution, but we have to be careful. We have to choose very carefully here. What becomes u? Which, remember, u is a function of x. If we pick the wrong u, we'll discover pretty quickly that we either don't have the right information to answer the question, or else we're just making it even messier. So we'll start here and we'll calculate du dx. So if we rewrite this as you can see that we're missing an 8 here. which we can supply ourselves by multiplying and dividing by 8. So in other words, we're going to supply our own constant. Call it supplying a constant. We need the 8, so we'll have 1/8 times this expression. And the reason why this is important is because what we have now is all of a sudden we have 1/8. This is radical u. This is now simply du. Or we should probably rewrite it as u to the 1/2 du. And the great thing about this is that we can now apply the power rule. So we'll have 1/8. So we'll have, when you add 1 to 1/2, you get 3/2. Evaluated from 1 to 3. But, we're dividing by 3/2 is the same thing as multiplying by 2/3. And just to keep it simple, we should probably just multiply together constants. So we have 2 out of 22 24ths. Which of course is the same thing as 1/12. Now we can replace the u with whatever definition we chose, which was 4x squared plus 9. And now what we have to do is, of course, evaluate it. So we'll keep the 1/12 on the outside. So we're going to evaluate this first at x equals 3. And what we're doing here, of course, is based on the fundamental theorem of calculus. Then we're going to subtract the same function evaluated when x equals 1. Okay, so it's not a nice problem. The problem is a little messy, but we can do it. So 4 times 9 is 36 plus 9. Here we have 4 plus 9, 13 to the 3/2. Okay, so let's simplify that again. Okay, so we can just pop these into our calculator. And let's see what we get. 45 to the 3/2 power is ooh, this is not a very nice number at all. You know what? I'll tell you what we're going to do. The 45, what you're actually doing there is you're taking 45, you're raising it to the 3rd power. And whatever you get there, you're taking its square root. So this is actually radical 91125. Same thing over here with the 13. You're cubing it. To get 2197, and then you're taking the square root of that result. Neither one of these is a perfect square. We're not going to get integers. So as messy as this thing looks, this is where we're going to stop. Okay, this is good enough. We can't really simplify it any further. All right, well, now that I've said that, let's make sure. No, I didn't think so. No, neither one of these results in an integer, so we'll just leave it like this. Okay. Wow. Now, what's going on here? All right. So we probably can't really do anything algebraically with it. Let's do this. Why don't we take a look and see if we let u equal 4x squared plus 9, what happens? All right, so this actually looks pretty promising because we only need to supply a constant. And we have our du. In other words, so that means what we can do is rewrite this as 1/8 du over u squared. And now we're in good shape because we can simply use the power rule. Although, in my opinion, it would be easier if you rewrite it like this. I don't know. That's just me. I would prefer to leave it like that only because we're trying to apply this power rule, which, so this is our n, and therefore, sorry. We'll end up with 1/8 u to the -1 over -1. This one is a indefinite integral, so we do need the c, but then we don't have to evaluate it. And so what we actually have here is -1/8 times u to the -1. And of course, we don't want to forget to replace the u with its definition. And that would be 4x squared plus 9. And that's your result. Okay. So, sometimes it's just a question of looking at it and saying, it's almost, but not quite where it needs to be in a convenient form. If the only issue we have is we're missing a constant, that's easy to deal with because we can simply supply it ourselves by multiplying and dividing by that constant. If something else is missing, like an x, well, that's a very different matter altogether. Okay. Oh, what's going on here? So again, it's a method of substitution problem. Let's try u equals, and in general, what you're looking for is let's find the messiest part of the expression first. And then if you're going to have u, don't include the exponent. Here, for example, I'm just going to have u equals 1 minus t squared. Because if I do include the exponent, I will not get the du that I need. Okay, so here, remember the variable is t. So this implies that du is minus 2t dt. And so I almost have that. I have t, but not negative 2t. Okay. So again, let me rewrite this a little so it's more clear that we can use this method of supplying a constant. And what I'm going to do is multiply out here by -1/2. And then I'm going to multiply here by -2. So that the product of these two, the -1/2 and the -2, end up being 1, which doesn't affect anything. I have to be careful here because that is actually the product of a negative number. We're not subtracting. So that means that based on what we've defined up at this point, we have u to the 10th du, which means, of course, we can use the power rule. And we do need the c. And u, of course, was 1 minus t squared. And to the 11th, that is, don't forget that exponent. And that's our final result. Well, all right then. Now this one looks like it's going to be very similar. Well, let's see how it works out. Let's not jump to any conclusions. Let's try u equals 7x minus 11. Du dx is 7. And therefore, du equals 7 dx. Well, what do you know? So you see, the thing is, we do have the ability to supply the constant we need, which is 7. So we're multiplying and dividing by 7. So now we have and now we can certainly apply the power rule. But again, now here we don't need the C. And so first we would need to replace the U with its definition. So remember, U way up here is 7x minus 11. And so we have this raised to the 5th over 5. And again, why don't we move that constant on the outside? Because it's just going to make things more awkward. And so now what we're going to do is evaluate it. First at 4. And then at minus 2. Oh, sorry, not what am I saying? No, this is the exponent is still 5, but it's the x that has been replaced with minus 2. Okay. So in other words, in the first case, this is what we would have called previously f of 4, meaning the integral evaluated when x equals 4. And then here we're doing the same thing with negative 2. Okay. And then we're subtracting them according to the fundamental theorem of calculus. So what do we have? 28 minus 11 to the 5th power minus 14 minus 11 to the 5th power (17 to the 5th minus 25 to the 5th. Okay. And let's see what's that. That is equal to. Actually, let me neaten this up a bit. All right. So 17 to the 5th is 141, 987. No, 141. Oh my God, it's even bigger than I thought. 1,419,857. So minus 25th to 5 to the 5th is negative 9765625. So you're actually adding those two numbers together because you have a double negative there. Yeah, this is a big number. All right, 1,419,857 plus 9765625, all divided by 5. Well, it's not an even amount. So I'll tell you, let's just leave it like this. The sum of the two is that's good enough. Okay. That'll do the job. Man, it's a big number, but remember, this is a 5th order polynomial. That's why it's such an enormous number. All right. Ooh, now we're back to these. So what's going on with this one? So remember here, our goal is to find e to the u du. So let's let u be the 2x, the exponent. Du dx is 2. Du is 2 dx. So we're missing a 2 here. And we know what to do. Well, oh, oops, sorry. No, that's not what we do. We multiply by half n by 2. So here's our du. This is e to the u. evaluated from 0 to 2. And so this is pretty straightforward because, as you know, the integral of e to the u du is simply e to the u plus c if it's an indefinite integral. So here we'll have 1/2 e to the u evaluated from 0 to 2. U is 2x. So we'll have 1/2 e to the 2 times 2 minus e to the 2 times 0. And then we just have to clean it up a little and simplify it. E to the 4th minus e to the 0. And of course, e to the 0 is just 1. And we're done. All right, so far so good. Now, what about this one? Now, it has that look to it. There's an x in the denominator. It appears that we're almost certainly going to end up with logarithms involved here. So here's what we could probably do. Why don't we, first of all, move this 2 on the outside. I'm rewriting it slightly like this. And of course, you may recognize right away that this is equal to 1/2 times the log of absolute x plus c. Okay, so this is one of our important results. It should be in this chart somewhere. If it's not, it's certainly in the slides. It's this one right here. Okay, this is 4D. So this is one of the ones you might want to think about making up a little chart of your own, just so you can quickly refer to it. I'm not so sure if it's even in here. It's almost like they went nuts with all the complicated ones. They left out maybe one of the simpler ones. Well, all right, anyway, let's get back to this. And again, this is an indefinite interval, so we need this constant. Ooh, now look at this. So let's try. Now you remind, if you go back to chapter 3, you might remember that the derivative of log of x is 1 over x. So I don't know if they have a chart for the derivatives. They probably do. But if you go back to the slides from way back in chapter 2, you should find it. And if you recall, I mean, if it's a function, like for example, that would be g prime of x over g of x. But since here g of x is simply x itself, that means that the derivative is just 1. Okay, so then that means that du equals dx over x. Now, if you look at this thing carefully, oh, so you actually have the integral u du. All right, it doesn't look like it when you first started out. If you just let u be log x, then du is, oh, wait a minute. No, I did it right. It's du, yes, that's right. So this is what we have, and then we can apply the power rule here. So we end up with log x squared over 2 plus c. Oh, wait a minute. No, no, that's right. Yep, no, I got it. U is log x, du is dx over x, so we're good. Now this one is a little different. Well, actually, no, it's not. Like, look what happens here. Let's try u equals negative x squared. Yeah, looks like all we need is to supply a constant. We need the negative 2. And so what we have here is, and again, I'm going to put parentheses here just to make sure it's obvious that this is not a subtraction. We're multiplying by a negative number. So we end up with negative a half e to the u du, which means negative a half e to the u plus c. And that's equal to negative a half e to the minus x squared plus c. Right. What about number 12? Now, this one really looks like a disaster in the making, but here's what we have to keep an eye on. The highest order of x here is above the highest order of x up here in the numerator. So why don't we try this? So, hmm, interesting. Turns out that the numerator is 1/3 of that. So I'm going to supply the constant of 3. And so that's exactly what we needed. Oh, I ran out of room for the dx. Okay, so in other words, what you've actually got here is 1/3 dx over x, sorry, du over u. And this is simply the log. Oh, I almost forgot. This one is a definite integral. Okay, we don't want to lose that. And so u, we originally chose that to be 3x plus 3x squared plus x cubed. And now we can simply evaluate it. Start with log of 3 times 2 plus 3 times 2 squared plus 2 cubed minus log 3 times 1 plus 3 times 1 squared plus 1 cubed. Okay. Um, we'll have a third log of 6 plus 12 plus 8 minus log 3 plus 3 plus 1. 1/3 log of 26 minus log 7. And that's it. We're done. Now, if you needed to know the exact value of this, you could plug it into your calculator, but this is fine. Now, this is one of those cases where you really kind of do need a chart. This is just a straight ahead definition. The integral of tan x is negative log of cosine u. In this case, we'll call it cosine x. Oh, wait a minute, what am I doing? The integral of tan x dx. Fix that. Okay, so according to this table, it's negative log x. So in this case, x, u is x. Okay. It's a simple function of x. So the integral of tan x dx is very simply negative log cosine x plus c. So that means here, all we have to do is evaluate this between, oh, we don't need the c in this case, but between 0 and pi over 4. So we'll have minus negative log cosine 0. Okay. So the cosine of pi over 4, we can go to our calculators. Okay, 0.70, which I think, let me just double check this. Yeah, it had that certain look to it. This is actually radical 2 over 2. Let me write it like that. It's just a little bit cleaner. Okay. And then this one is now the cosine of 0 is 1. So we're going to have minus minus log, which means plus. Oh, okay. Well, now, of course, the log of 1 is just 0. So we ultimately just end up with minus log radical 2 over 2. Okay, because this is just 0. All right. Okay, let's go. What's going on here? Oh, see now look at this one. This is an interesting case. What if I tried u equals 1 minus x squared? Oh, see now I'm not missing just a constant. I need a negative 2x up there. And I don't have that. I can supply a constant, but I can't supply an x. So that means this is not the correct approach. So what it makes me think of is that it may be one of those arc sine, cosine functions, one of those. Let's go back and look at our chart for a second. It looks like it's in square root. Here it is. Um, Actually, I'll tell you what, let's go back to our slides for this. Only because I had them all together nicely, neatly. It's this one. All right. Let's copy it. Yeah, it's like I just would rather have them all together in one place. I just would like to copy this here so we can see it. Okay, and then this got moved in here. Hold on. All right. So if you look at these together, um, you can see that if this is a squared and this is minus u squared, that implies that a is 1 and u is x. And du would be dx, since u is just x. So we're good. So we end up with the arc sine. Now keep in mind too, this is a definite integral. We don't want to forget about that, which runs from 0 to the radical 3 over 2 of, okay, I guess I'll just copy the whole thing again. Dx over radical 1 minus x squared, where we've already determined that a is 1 and u is x. So we end up with arc sine. U is x. Now a is 1, so the absolute value is irrelevant. We don't need the c because, of course, this is a definite integral. So, oh, and of course, this whole thing has to be evaluated from 0 up to radical 3 over 2. So we've got the arc sine of x from 0. Oh, what did I do? It's radical 3 over 2. I don't know why I wrote that. Okay, so we've got the arc sine of radical 3 over 2 minus the arc sine of 0. Now, your calculator has this function. It's directly above the trig functions. In other words, arc sine is the second function of arc sine. So we'll go ask for second sine, and then we'll ask for radical 3 over 2. We're going to have to be careful entering this one. Hold on 1 second. Ooh, I got 104,719, whatever that is. And the arc sine of 0 is 0. It's probably something like it might be, for example, 7 pi over 6 radians, something along those lines. But anyway, this is the final result. And then now this last one, you can see it has that sort of look to it. You can see that if I try to use the method of substitution, it won't work because I don't have 2x dx. I can't just supply it. I can supply the 2, but not the x. So we need to look at our chart again. And we'll look at my chart because you can see this is the one that corresponds to the arc tangent. So it's just a squared plus u squared. So that implies that a squared is 9 means that a equals 3, and u squared equals x squared, which implies that u equals x. So we end up with 1/3 arctangent x over 3 plus the constant. This one we don't have to evaluate. It's a definite integral. So yeah, see, after a while, so you try the method of substitution, you see that it doesn't work, then you look for something else. So far we haven't really covered that many different techniques. So if it's not the method of substitution, then there's a decent chance it might be one of these bizarre arc sine or arc cosine functions. Now later on, of course, we'll go through and keep expanding our integration skills, and we'll learn more and more complex techniques for more and more complicated cases. But for now, for chapter 4, this is obviously not a complete set of problems that you could run into, but it's a very good representation of them. So if you can do these, you'll be in pretty good shape. Okay. So anyway, all right, so we'll stop here. Now we're going to move ahead after this to chapter 5. We're basically going to go back and revisit logs and exponential functions. We're going to treat them more formally, and we'll tie them together and see how their derivatives work, how their integrals work. And also we'll be looking at a few other types of functions. But so that's what's coming up in chapter 5. All right. So anyway, I'll see you all next time.